Hello, in this lecture we'll find out the length of line segment X using two different methods. In the drawing we have a semicircle inside a quarter circle. We note that side AO equals to 6 units and the side AC is tangent to this semicircle at this point, and we want to find out the length of side AC that is equal to X. So we start with the first method and we will define the center of this semicircle as point P, and we will define the point of tendency of tangent AC in this semicircle as point D. And here, because of the fact that AOB is a quarter circle, it means that this angle AOB, must be equal to 90 degrees, and also point O must be the center of this quarter circle. And so here point O is the center of the quarter circle, and point A is a point on the quarter circle itself, and this is exactly the definition of a radius. That is to say, the radius of the quarter circle equals to 6 units. So here, for the same reason, exactly OB is also the radius of the quarter circle. That is to say, it is equal to 6 units. Why? Because it starts from the center of the quarter circle and then at point B, that is a point on the quarter circle itself. But OB is not only the radius of the quarter circle, but it is also the diameter of the semicircle. So the diameter of the semicircle equals to 6 units. Therefore, the radius of the semicircle will be equal to half of it. That is to say, the radius of the quarter circle will be equal to 6 over 2, that is 3 units. So here, PB, line segment PB, P is the center of the semicircle and B is a point of the semicircle itself. That is to say, PB is the radius of the semicircle, that is to say, it is equal to 3 units. And PO is also the radius of the semicircle, that is to say, this also equals to 3 units. We will join points P and D together by a straight line. Here, line segment PD is also the radius of the quarter circle because of the fact that it starts from the center of the quarter circle and ends at point D, that is a point on the quarter circle itself. And this is exactly the definition of a radius. So PD is the radius of the quarter circle, that is equal to 3 units. In the next step, we will join points A and P together by a straight line. And I will present to you a new rule, that is rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So I write it down. The lengths of two tangents from a common external point to a circle are equal. So I read rule number 1 again. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this point P, this point P, is defined as an external point in relation to this circle. Why point P is an external point? Because point P is not located inside this circle, nor on this circle, but it is located outside the circle. For that reason, it is defined as an external point. So if from the external point P we draw two tangents to this circle, so the first tangent, this is the first tangent, here the point of tendency of the first tangent with this circle is at this point A, and we will draw a second tangent. Here the point of tendency of this tangent, the second tangent with this circle, is at point B. And according to rule number 1, the lengths of two tangents, that is to say, the first tangent is tangent PA, and the second tangent is tangent PB. So the length of two tangents from a common external point, the common external point is point P, to a circle, 2 points A and B are equal. That is to say, PA equals to PB. So the lengths of those two tangents are equal to each other, which means the PA equals to PB. So whenever you have a common external point of a circle and you draw two tangents to that circle, then the lengths of those two tangents will be equal to each other according to rule number 1. So we actually can implement rule number 1 in our drawing, because in our drawing we have the common external point A, and from the common external point A we have two tangents to this semicircle. The first tangent is tangent AO, and the second tangent is tangent AD. And according to rule number 1, the lengths of those two tangents must be equal to each other. So we can write down that here tangent AO is equal to tangent AD according to rule number 1. AO equals to AD according to rule number 1. Okay? But AO equals to 6 units according to what is given us in the question. Here AO equals to 6 units. It is given us in the question. So from this equation, 6 equals to AO equals to AD. We will derive that AD is also equals to 6 units. Here AD equals to 6 units. So we can write down in the drawing that AD, this line segment AD is equal to 6 units in its length. In the next step, we will prove that the right triangle AOP, this right main triangle, triangle AOP, is congruent to the right triangle APD. This right main triangle, triangle APD. And those two right triangles congruent to each other according to side rule. So I write it down. Triangle AOP congruent to triangle APD. This is the sign of congruent. Triangle AOP congruent to triangle APD. According to side rule. So why those two triangles congruent to each other? First of all, side AO equals to side AD equals to 6 units according to rule number 1. AO equals to AD equals to 6 units. In addition, side AP is a common side, it belongs to both triangles. So we can write down that side AP equals to itself. It's a common side that belongs to both triangles. And finally, side OP equals to side PD equals to 3 units. OP equals to PD equals to 3 units. This is the radius of the semicircle. So we actually proved that all the sides of triangle AOP can run to all the sides of triangle APD. Therefore, those two triangles can run to each other according to side rule. And from the fact that those two triangles can run to each other, we will derive that those two angles are equal to each other. That is to say, angle OAP this angle is equal to this angle, that is actually angle PAD, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can congruent to each other, therefore those two corresponding angles must be equal to each other. Okay? So if we define angle OAP as theta, here angle OAP equals to theta according to our definition. Angle OAP equals to theta. Then from this equation, theta equals to angle OAP equals to angle PAD, we will derive that angle PAD is also equals to theta. Angle PAD is also equals to theta. So those two angles, they are both equal to theta. In the next step, we will join together points O and C by a straight line. So, by joining those 2 points together, we created here triangle AOC. But before that, we will focus on the right triangle, the right green triangle, triangle AOP. On the right green triangle, triangle AOP. This green right triangle, we know that tangent theta equals to OP over OA. And repeat again. In the right green triangle, triangle AOP, tangent theta equals to OP over OA. Here OP equals to 3 units. And OA equals to 6 units according to what is given us in the question. So actually, in conclusion, we found out that tangent theta equals to 3 over 6. Here we'll divide both the numerator and the denominator on this side of the equation by 3. And we get that in conclusion, tangent theta equals to 3 over 3 is 1 and 6 over 3 is 2. So in conclusion, we found out that tangent theta equals to 1/2. Tangent theta equals to 1/2. In the next step, I will present to you a new law that I've already mentioned it, that is the law of cosines, and we will implement the law of cosines in this triangle, triangle AOC. So what is the law of cosines? The law of cosines is true in any triangle. So actually, if we have a triangle ABC, that could be any triangle, this is triangle ABC. The length of side AB in triangle ABC is A units. The length of side AC of triangle ABC is B units. And side BC equals to C units in its length. And the angle between side AB and side AC is alpha. Then according to the law of cosines, C squared equals to A squared plus B squared minus 2 times A times B times cosine alpha. I'll repeat again, in any triangle, this equation is true that C squared equals to A squared plus B squared minus 2 times A times B times cosine alpha. So we will implement the law of cosines in this triangle, triangle AOC. So we'll copy the triangle AOC in the new page and we will implement the law of cosines in this triangle, triangle AOC. Side AO equals to 6 units according to what is given as the question. And what is the length of side OC? O is the center of the quarter circle. C is the point of the quarter circle itself. And this is exactly the definition of a radius. That is to say, OC is the radius of the quarter circle that is equal to 6 units. Okay, OC equals to 6 units. And AC equals to X, that is the line segment that we are looking for. And angle OAC, this angle equals to theta plus theta, that is 2 theta. So this is triangle AOC that I copied from the original drawing. This side. See? So now we will implement the law of cosines in this triangle, triangle AOC. According to the law of cosines, this will be equation number 1. According to the law of cosines, we get that OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. Okay, again, OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. This is equation number 1. Here OC equals to 6 units, therefore OC squared is 6 squared, that is 36. And it is equal to AC squared, AO squared. AO equals to 6 units, therefore AO squared is equal to 6 squared, that is 36, plus AC squared. AC equals to X, therefore AC squared is X squared, minus 2 times AC equals to AO equals to 6, AC equals to X times cosine 2 theta. Okay, so here we have 36 on both sides of equation number 1, so 36 will get cancelled. So in this side, what is left after we cancel 36, what is left is 0, and it is equal to X squared minus 2 times 6 is minus 12. So this expression equals to minus 12 X times cosine 2 theta here we will add to this equation number 1 12x cosine 2 theta, and we will get that according to equation number 1 12x cosine 2 theta equals to x squared. Here we will divide this equation number 1 by x. It is allowable to divide this equation number 1 by x because x is the length of side AC. It can never be equal to 0. For that reason, it is allowable to divide this equation number 1 by x. So we divided this equation by x, so here x will get cancelled, and we left only with 12 times cosine 2 theta, that is equal to x squared over x is x. So in conclusion, we found out that according to equation number 1, 12 times cosine 2 theta equals to x. So the only thing that is left to do in order to find out the value of x, the line segment that we are looking for in this lecture, is to find out the value of cosine 2 theta. we have trigonometric identity for cosine 2 theta. According to the following trigonometric identity, cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. Okay, I repeat again, according to this trigonometric identity, cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. But we have already found out that tangent theta equals to 1 half. Here, we have already found out that tangent theta equals to 1 half. Now we can substitute tangent theta in this trigonometric identity by 1 half. We'll do it now, and we'll get here that cosine 2 theta equals to 1 minus tangent square theta. If tangent theta equals to 1 half, then tangent square theta will be equal to 1 half squared over 1 plus tangent square theta, that is 1 half squared. So here we found out that cosine 2 theta equals to 1 minus 1 half squared. 1 half squared is 1/4 over 1 plus 1 half squared, that is 1/4. If 1 minus 1/4 is 3/4, and 1 plus 1/4 is 5/4. So in conclusion, we found out that cosine 2 theta equals to 3/4 over 5/4. Here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled. And finally, in conclusion, we found out that cosine 2 theta equals to 3 over 5, that is 3/5. Cosine 2 theta equals to 3/5. According to equation number 1, we found out that 12 times cosine 2 theta equals to x. Now we can substitute cosine 2 theta by 3/5. We will do it now, and we will get that according to equation number 1, 12 times cosine 2 theta is 3/5 equals to x. So x equals to 12 times 3 is 36 over 5. 36 over 5 is 7.2 units. 7.2 units. So in conclusion, we found out that x, that is also equals to AC, it is equal to 7.2 units. Here, x, that is equal to also to AC, it is equal to 7.2 units. Okay, we finished with the first method. In the next step, I will present to you how to find out the length of line segment AC that is equal to x according to the second method. In the second method, we will use all the things that we have already found out in the first method. Here, the center of the semicircle is at point P. The point of tendency of tangent AC with this semicircle is at point D. We have already found out that here PD is the radius of the semicircle that is equal to 3 units. OP is also equals to 3 and PB equals to 3. All are the radii of the semicircle. This angle equals to 90 degrees. It is a right angle. The radius of the quarter circle is equal to 6 units. Here we join together points A and P in the first method. And we have already found out that those two triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we concluded that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. And then, if this angle equals to theta, then this angle must be also equal to theta because of the fact that they are equal to each other. So those two angles, they are both equal to theta according to what we have already found out in the first method. Okay, so all the things that we did until now, we've already done in the first method. From now, we will do another construction in the second method. In the second method, we will extend line segment AC and line segment OP by a straight line until they intersect with each other. And we will define the intersection point between the extended line segment AC and the extended line segment OB as E. Okay? So here we created a right triangle, triangle AOE. In the right triangle, triangle AOE, this angle equals 90 degrees. And we have line segment AP bisects angle OAE into two halves. Each half equals to theta. For that reason, line segment AP is defined as angle bisector. Therefore, we can implement the angle bisector theorem in this right triangle, triangle AOE. So first of all, I will present to you what is the angle bisector theorem, and only after that we will implement the angle bisector theorem in this right triangle, triangle AOE. Okay, so what is angle bisector theorem? Angle bisector theorem is true in any triangle. So here I write it down, angle bisector theorem. So actually, if we have triangle ABC, that could be any triangle. This is triangle ABC. And we have line segment AD divides angle BAC into two halves. Each half equals to theta. For that reason, line segment AD is defined as angle bisector. So you can write here that line segment AD is angle bisector. Why? Because it divides angle BAC into two halves. So according to angle bisector theorem, the angle bisector in a triangle, in our specific example, the angle bisector is AD, so we write in brackets that we are relating to line segment AD, that it is the angle bisector in this triangle ABC, because it bisects angle BAC into two halves. So AD is the angle bisector in this triangle ABC. So the angle bisector in a triangle divides the side that it is, divides the side that it is, in this case, angle bisector AD is side BC. So we can write here that in our specific example, we are relating to side BC. So actually, angle bisector AD divides side BC into two halves, into two parts. The first part is BD, and the second part is DC. So the angle bisector in a triangle divides the side that it is in a ratio I repeat again that the angle bisector AD divides side BC into two parts. The first part is BD and the second part is DC, and the ratio between those two parts is BD over DC. Okay? So the angle bisector AD divides side BC into a ratio that is equal to BD over DC, but this ratio, it is equal, that is equal to the ratio between the angles legs. We are relating here to the legs of the angle that has been bisected, that has been divided into two parts. That is to say, we are relating to angle BAC. Angle BAC has two legs. The first leg is AB and the second leg is AC. And the ratio of those two legs is AB over AC. AB over AC. So the ratio between the angles legs is AB over AC, and that ratio is equal to the ratio that angle bisector AD divides side BC. And the ratio that angle bisector AD divides side BC is BD over DC. In conclusion, we found out that according to angle bisector theorem, in triangle ABC, AB over AC equals to BD over DC. Again, according to the angle bisector theorem, the angle bisector AD divides the side that it is. Angle bisector AD is side BC, and divides it into two parts. The first part is BD, and the second part is DC. And the ratio between those two parts is BD over DC, and that ratio equals to the ratio between the angles legs. We are relating here to the legs of the angle that has been bisected by the angle bisector ID, that is to say, we are relating to angle BAC. Angle BAC has two legs. The first leg is AB, and the second leg is AC. And the ratio between those two legs is AB over AC. And that ratio between those two legs, that is AB over AC, equals to the ratio that angle bisector AD divides side BC. And the ratio that angle bisector AD divides side BC is BD over DC. And this ratio equals to the ratio between the angles legs, that is AB over AC. In conclusion, according to angle bisector theorem, in the right triangle ABC, AB over AC equals to BD over DC. So that is the angle bisector theorem. Now we can implement the angle bisector theorem in the right triangle, triangle AOD. Why? Because we have side AP that is defined as angle bisector. Side AP that is angle bisector divides side angle AOE into two halves. Each half equals to theta. So I copy the right triangle AOE in a new page, and we will implement the angle bisector theorem in this right triangle, triangle AOE. Okay? Side OA equals to 6 units according to what is given as the question. And here we have the angle bisector AP. That divides angle OAE into two halves. Each half equals to theta. And OP is the radius of the semicircle, that is equal to 4 units. So this is the right triangle, triangle AOE that I copied from the original drawing. In this right triangle, triangle AOE, we will implement the angle bisector theorem. According to angle bisector theorem, the angle bisector AP divides the side that it is, that is to say angle bisector AP each side OE, and divides this into two parts. The first part is OP, and the second part is PE. And the ratio between those two parts is OP over PE, and that ratio equals to the ratio of the angles legs. We are talking about angle OAE that has been bisected into two halves, and the legs of angle AOE is AO and AE. And the ratio between those two legs is AO over AE. So the ratio between the two legs is equal to the ratio that angle angle bisector AP divides side OE. That is OP over PE equals to AO over AE. This is the implementation of angle bisector theorem in the right triangle AOE. So OP, according to equation number 1, OP equals to 3 units over PE, and it is equal to AO. AO equals to 6 units according to what is given as the question, over AE. Here we'll divide equation number 1 by 3 and we'll multiply it by AE. And we'll get that according to equation number 1, 6 over 3, that is 2, is equals to AE over PE. According to equation number 1, 6 over 3 is 2, and it is equal to AE over PE. Here we multiply equation number 1 by PE, and we get that according to equation number 1, AE equals to 2 times PE. So AE is twice as long as PE. We define PE as A. So PA equals to A according to our definition. Here PA equals to A. And the original, so we write down that PE equals to A according to our definition. Now we can substitute PE by A in equation number 1. We'll do it now and we'll get that AE equals to 2 times PE, and PE equals to A, so therefore AE will be equal to 2 times A according to equation number 1. So AE equals to 2A. We can write down here that AE, side AE, equals to 2A. And in the next step, we will implement the Pythagoras theorem on the same right triangle AOE. Okay, so I will copy the right triangle AOE in a new page and we will implement the Pythagoras theorem on this right triangle AOE. Here, side OE, from the drawing you can see that side OE equals to 3 plus A. OE equals to 3 plus A. So you can write here that OE equals to 3 plus A. AO equals to 6 units according to what is given as the question. And here AE equals to 2A according to equation number 1. A equals to 2A according to equation number 1. So this is the right triangle AOE that I copied from the original drawing, and we'll implement the Pythagoras theorem on this right triangle, triangle AOE. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here, this will be question number 2. The hypotenuse is AE, the square of the hypotenuse is AE squared, and it is equal to the square to the sum of the squares of the perpendiculars. That is to say, it is equal to AO squared plus OE squared. So AE equals to 2A, so therefore AE squared is 2A squared. Here AO equals to 6 units, therefore AO squared is 6 squared, that is 36, plus OE squared. OE equals to 3 plus A, therefore OE squared equals to 3 plus A squared. Here we will open the brackets on both sides of equation number 2, and we get that according to equation number 2, A squared is 4A squared, and it is equal to 36 plus 3 plus A squared. 3 plus A squared equals to 3 squared, that is 9, plus A squared plus 6A. So 4A squared, according to equation number 2, 4A squared equals to 36 plus 9 is 45, plus A squared plus 6A. Here we'll subtract A squared from this equation, equation number 2, and we get that according to equation number 2, 4A squared minus A squared is 3A squared, and it is equal to 45 plus 6A. Here we will divide this equation, equation number 2, by 3, and we will get that according to equation number 2, 3A squared over 3 is A squared, and it is equal to 45 over 3 is 15, and 6A over 3 is 2A. So here we subtract 15 and also 2A from this equation, equation number 2, and we get that according to equation number 2, A squared minus 2A minus 15 equals to 0. So here we have a quadratic equation, and the coefficient A in this quadratic equation equals to 1, the coefficient B equals to minus 2, and the coefficient C equals to minus 15, and the variable that we are looking for is A in this quadratic equation, so x equals to A, and the general formula to solve a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. So we put the data inside this general formula, and we find out the value of the values of a, because x equals to a here. So a equals to minus b, b equals to minus 2, so minus b is minus 2, that is plus 2, plus minus square root of b squared. B equals to minus 2, so b squared is minus 2 squared, that is 4. Minus 4 times a is 1, times c is minus 15 over 2a. A is 1, so 2a is 2 times 1, that is 2. So here a equals to 2 plus minus square root of minus 4 times minus 15 is plus 60, and 60 plus 4 is 64. So inside the root we have only 64 that is left. So it is all divided by 2. So here we found out that a equals to 2 plus minus, the square root of 64 is 8 over 2. So here we will have two solutions that are possible from a. The first solution from a is that a equals to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. Okay, so we found out that according to the first solution, a equals to minus 3, that is a negative number. But here, from the drawing, you can see that a is the length of side PE. Therefore, a as a length must be a positive number. A is a length, therefore it must be a positive number. Therefore, it can never be equal to minus 3, that is a negative number, so we cancel this solution, and we left only with the solution that the second solution, that a equals to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So we found out that a equals to 5 units. Here a equals to 5 units. So we can write here that a equals to 5 units. If a equals to 5 units, then 2a is 2 times 5, that is 10 units. So AE equals to 2a, and it is equals to 10 units, and PE equals to a, that is equal to 5 units. In the next step, we will find out the length of line segment BE. From the drawing, it is very easy to see that the length of line segment BE, it is equal to PE minus PB. PE minus PB. I'll repeat again. The length of line segment BE is PE minus BP, PE minus PB. So BE equals to PE equals to A, that is equal to 5 units, minus PB equals to 3 units. This is the radius of the semicircle. So in conclusion, we found out that BE equals to 5 minus 3, that is 2. So BE equals to 2 units. So we can write here that BE equals to 2 units. In the next step, we will find out the length of side CE. Okay, CE from the drawing, it is very easy to see that CE equals to AE minus AC. I repeat again, CE equals to AE minus AC. Okay, CE equals to AE minus AC. So CE equals to AE. Here AE equals to 10. A equals to 10. And AC, it is the line segment that we are looking for. It is equal to X according to what is given us the question. So, in conclusion, we found out that CE equals to 10 minus X. Here CE equals to 10 minus X. You can write here that C equals to 10 minus X. In the next step, we will complete the quarter circle to a circle. So we completed the quarter circle to a circle, and then we will extend line segment BO by straight line until it touches the circle. Okay. And we define the touching point of the extended line segment OB in the circle as point M. So what is the length of line segment MO? O is the center of the quarter circle and also the center of the circle itself. M is a point on the circle itself, and this is exactly the definition of a radius. That is to say, MO is the radius of the circle, that is also the radius of the quarter circle, that is to say, it is equal to 6 units. Okay? So, in the next step, I will present to you a new rule, that is actually rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, then the following equation is true. So, actually, outside the circle, we have this point P is located outside the circle, and we have actually point P is the intersection point of the two chords, so you write it down. Point P is the intersection point for the two chords. So here we have the first chord is called AB. This is chord AB that intersects with chord CD. This is chord CD. So here chord AB intersects with chord CD, it's point P. Point P is the intersection point between those two chords. So if this is the data that has been given to us, then according to rule number 3, the following equation is true. PA times PB, PA times PB equals to PC times PD. Okay, I repeat again. If chord AB intersects with chord CD at point P is the intersection point of chord AB with chord CD, then so they're intersecting with each other outside the circle, then according to rule number 3, the following equation is true, that PA times PB equals to PC times PD. I'll repeat again. If we have this circle, and in this circle we have two chords, chord AB and chord CD. And those two chords intersect with each other outside the circle at point P. Point P is the intersection point of chord AB with chord CD. Then, if this the data that has been given to us, then the following equation is true, that PA times PB equals to PC times CD. So this is rule number 3. We can implement rule number 3 in our drawing, because in our drawing we have chord AC, this chord AC intersects with chord MB at point E. Point E is the intersection point. So I write it down, chord AC this chord called AC intersects with chord MB at point E. I repeat again. In our drawing, chord AC intersects with chord MB at point E. Point E is the intersection point of chord AC with chord MB. Therefore, we can implement rule number 3 in our drawing. Therefore, according to rule number 3, we get that EC times EA equals to EB times EM. I repeat again, according to rule number 3, EC times EA equals to EB times EM. Here, according to rule number 3, EC times EA equals to EB times EM. Okay? So, EC equals to 10 minus X, EA equals to 10 units, EB equals to 2 units, and EM, the long line segment EM equals to 6 plus 3 plus 3, that is 12, plus 2, that is 14. In conclusion, we found out that EM equals to 14 units. So, actually, we found out that according to rule number 3, 10 minus X times 10 equals to 2 times 14. 2 times 14 is 28. So 28 equals to 10 times 10 minus X. Here we will divide this equation by 10, and we get that according to this equation, 10 minus X equals to 28 over 10 is 2.8. Here we relate to this equation X, and we subtract 2.8, and we get that X equals to 10 minus 2.8. 10 minus 2.8 is 7.2 units. So we found out that AC, that is actually equals to X, it is equals to 7.2 units. Okay, so here AC, that is equal to X, it is equal to 7.2 units. So in both methods we arrive to the same answer, to the same result for X, that is equal to 7.2 units. In the next step I will summarize the lecture. We'll start with the first method. First of all, I'll repeat on the question. In the drawing, we have a semicircle that is inscribed by a quarter circle, or a semicircle is inside a quarter circle. We know that side AO equals to 6 units. Side AC is tangent to the semicircle at this point, and we want to find out the length of side AC, that is actually equals to X. Okay, so first of all we define the center of the semicircle as point P, and we define the point of tangency of tangent AC with this semicircle as point D. And because of the fact that we have here quarter circle, AOB is a quarter circle, this angle must be equal to 90 degrees, angle OAB must be equal to 90 degrees, and point O must be the center of the quarter circle. So if point O is the center of the quarter circle, and point A is a point of the quarter circle itself, therefore AO is the radius of the quarter circle. And we know that the radius of the quarter circle AO equals to 6 units, therefore the radius of the quarter circle equals to 6 units. and OB, it is also the radius of the quarter circle, because it starts from the center of the quarter circle and that's at point B, that is the point of the quarter circle itself. That is to say, it is the radius of the quarter circle that is equal to 6 units. But OB, it is not only the radius of the quarter circle, but it is also the diameter of the semicircle. So if the diameter of the semicircle equals to 6 units, then the radius of this semicircle must be equal to half of it, that is 6 over 2 is 3. See, so here OP, that is equal to PB, that is also equals to PD, all are the radii of the semicircle, and therefore they are equal to 3 units. That is half of the diameter, that is 6 units. Why the radii of the semicircle? Because of the fact that they start from the center of the semicircle and then at any point on the semicircle itself, and this is exactly the definition of a radius. Okay, so PO equals to PB equals to PD equals to 3 units. All those line segments are the radii of the semicircle that is equal to 3 units. In the next step, we join points A and P together by a straight line. And I presented to you a new rule, that is rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So if we have this circle and we have the external point, point P, from point P we have two tangents to this circle. The first tangent is tangent PA, and the second tangent is tangent PB. And according to rule number 1, the length of two tangents, that is to say, the first tangent is tangent PA, the second tangent is tangent PB, from a common external point, that is to say, from the common external point P to a circle, to points A and B are equal. That is to say, PA equals to PB according to rule number 1. So whenever you draw two tangents to a circle from a common external point to that circle, then the lengths of those two tangents will be equal to each other. In this case, PA equals to PB. So we can implement rule number 1 in our drawing, because in our drawing we have the common external point, point A, and from the common external point, point A, we have two tangents to this semicircle. The first tangent is tangent AO, and the second tangent is tangent AC. And the lengths of those two tangents must be equal to each other according to rule number 1. So here AO equals to AD according to rule number 1. But here AO equals to 6 units. AO equals to 6 units. So from this equation 6 equals to AO equals to AD, we will derive that AD is also equals to 6 units. So here AD equals to 6 units. Then we actually proved that those two right-angled triangles can go into each other according to side rule. So why they can go into each other? First of all, side AO equals to side AD equals to 6 units according to rule number 1. AP equals to itself, it is a common side that belongs to both triangles, and OP equals to PD equals to 3 units, it is the radius of the semicircle. So all the sides of triangle AOP can go into all the sides of triangle AOP, therefore those two triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we conclude that those two angles are equal to each other. That is to say, angle OAP equals to angle PAD according to the rule that corresponding angles in congruent triangles are equal to each other. Those two right-angled triangles can go into each other, therefore the two corresponding angles must be also equal to each other. So if we define angle OAP as theta, this angle equals to theta according to our definition, then from this equation theta equals to angle OAP equals to angle PAD, we will derive that angle PAD is also equals to theta. Okay, we will derive that angle PAD is also equals to theta. Yeah, this angle PAD is also equals to theta. So those two angles are both equal to theta. Then We join points O and C together by a straight line. Then we focus on the right triangle AOP, the right triangle AOP. The right triangle AOP, we know that tangent theta equals to OP over AO. The right triangle AOP, tangent theta equals to OP over OA. Here OP equals to 3 units, AO equals to 6 units. So in conclusion, we found out that tangent theta equals to 3 over 6. We divided both the numerator and the denominator of this expression by 3, and we found out that tangent theta equals to 3 over 3 is 1 and 6 over 3 is 2. So in conclusion, we found out that tangent theta equals to 1 half. Okay, then we implemented the Pythagoras theorem on the right on triangle AOC. But first we implemented the law of cosines in this triangle AOC. So what is the law of cosines? The law of cosines is true in any triangle. So if we have this triangle ABC, that could be any triangle. Side AB equals to A units in its length, side AC equals to B units in its length, and side BC equals to C units in its length. And the angle between side AB and side AC is alpha. Then according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine alpha. And then we implemented the law of cosines in triangle AOC. So here we have this triangle AOC that I copied from the original drawing. What is the length of OC? O is the center of the quarter circle. C is the point of the quarter circle itself. And this is exactly the definition of a radius. That is to say, CO is the radius of the quarter circle that is equal to 6 units. So here CO equals to 6 units. AO equals to 6 units according to what is given as the question. And AC equals to X. That is the line segment that we are looking for in this lecture. And the angle OAC equals to theta plus theta, that is 2 theta. So we implemented the law of cosines in this triangle AOC. According to the law of cosines, we get that OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. Okay, and here OC equals to 6 units, therefore OC squared is 6 squared, that is 36. AO is also equal to 6 units, so AO squared is 6 squared, that is 36 also, plus AC squared. AC is X, so AC squared is X squared, minus 2 times AO, that is 6, times AC, that is X, times cosine 2 theta. So here we have 36 on both sides of equation number 1, so 36 will get cancelled. So in this side of equation number 1 we have 0, that is equal to x squared, minus 2 times 6 is minus 12, so this expression, in conclusion, in total, it is equal to minus 12x times cosine 2 theta. So in conclusion, we found out that according to equation number 1, 0 equals to x squared minus 2x cosine 2 theta. We added 2x cosine 2 theta to this equation number 1, and we got that according to equation number 1, 12x times cosine 2 theta equals to x squared. We divided this equation number 1 by x, and we found out that 12 times cosine 2 theta equals to x squared over x is x. So according to equation number 1, 12 times cosine 2 theta equals to x. So the only thing that is left to do is to find out the value of cosine 2 theta in order to find out the value of the line segment that we are looking for, that is line segment x. So we find out the value of cosine 2 theta according to the trigonometric identity. Cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. We have already found out that tangent theta equals to 1 half, so we can substitute tangent theta by 1 half in this trigonometric identity. We did it, and we got that cosine 2 theta equals to 1 minus tangent square theta. Here, tangent theta equals to 1 half, so tangent square theta will be equal to 1 half squared. So here, cosine 2 theta equals to 1 minus tangent square theta, that is half squared, over 1 plus tangent square theta, that is 1 plus half squared, because tangent theta equals to half squared. And here we found out that half squared is 1/4. So here we found out that cosine 2 theta equals to 1 minus half squared, that is 1/4, over 1 plus 1/4, that is actually 1 square. Tangent theta squared, half squared. Half squared, 1 half squared is 1 square. So in conclusion, we found out that cosine 2 theta equals to 1 minus 1/4 over 1 plus 1/4. 1 minus 1/4 is 3/4, and 1 plus 1/4 is 5/4. So we found out that cosine 2 theta equals to 3/4 over 5/4. Here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled. And we conclusion, we found out that cosine theta equals to 3/5. And according to equation number 1, 12 times cosine 2 theta equals to x. Now we can substitute cosine 2 theta by 3/5. We did it, and we found out that cosine 2 theta is 3/5. That is equal to x. So 12 times 3 is 36. So we got that 36 over 5 equals to x. 36 over 5 is 7.2. So in conclusion, we found out that x that is equal to AC, it is equal to 7.2 units. We finished with the first method. In the next step, I will present to you how we found out the length of line segment AC that is equal to x according to the second method. In the second method, we used with all the things we already found out in the first method. Here we know that this angle equals to 90 degrees. Point O is the center of the quarter circle. The radius of the quarter circle is 6 units, and the radius of the semicircle is 3 units. P is the center of the semicircle. D is the point of tendency of tangent AC with the semicircle. OP equals to PB equals to PD equals to 3 units. This is the radius of the semicircle. We join points A and P together by a straight line. So those two triangles can go into each other according to side rule. We already found it in the first method. And for the fact that those two triangles can go into each other, we will derive that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if that one angle equals to theta, then the other angle must be also equal to theta. All those things we have already done in the first method. Okay? So I will not repeat on it. Then we extended line segment AC and line segment OB by a straight line until they intersect with each other at point E. Point E is the intersection point of the extended line segment AC and the extended line segment OB. So in this way, we created the right triangle AOE. In this right triangle AOE, we have line segment AP that divides angle OAE into 2 halves. Each half equals to theta, therefore AP is angle bisector of triangle AOE, therefore we can implement the angle bisector AOE in triangle AOE. We can implement the angle bisector theorem in triangle AOE, because AP is the angle bisector. So what is angle bisector theorem? The angle bisector theorem says that if we have this triangle, triangle ABC that could be any triangle, then and AD is the angle bisector. Why AD is the angle bisector? Because it divides angle BAC into 2 halves. Each half equals to theta. Therefore, AD is the angle bisector of triangle ABC. And according to angle bisector theorem, the angle bisector in a triangle, in this case is AD is the angle bisector, divides the side that it eats. Angle bisector AD eats side BC. So we are relating to side BC. So the angle bisector AD divides the side that it eats in a ratio. So the angle bisector AD eats side BC and divides it into two parts. The first part is BD, the second part is DC. And the ratio between those two parts is BD over DC. And that ratio is equal to the ratio between the angle's legs. We are relating to the angle that has been bisected by the angle bisector. That is to say, we are relating to angle BAC. Angle BAC has two legs. The first leg is AB, the second leg is AC, and the ratio between those two legs is AB over AC. That ratio, AB over C, equals to the ratio that angle bisector AD divides side BC. And that ratio equals to dB over DC. That is to say, in conclusion, that AB over AC equals to dB over DC. Okay, now we can implement rule number angle bisector theorem in our triangle AOC, or I repeat again on the angle bisector theorem. The angle bisector AD eats side BC and divides side BC in a ratio that is BD over DC, and that ratio equals to the ratio of the angle's legs. The ratio of the angle's legs is AB over AC. That ratio, AB over AC, equals to the ratio that angle bisector AD divides side BC. And this ratio is dB over DC. So in conclusion, AB over AC equals to dB over DC. We can implement angle bisector theorem in our in the right triangle AOE. So I copied the right triangle AOE in this new page, and we implemented the angle bisector theorem on this right triangle AOE. So the angle bisector AP in this right triangle AOE divides the side that it is, divides side OP into two parts. The first part is OP, the second part is PE. And the ratio between those two parts is OP over PE. And that ratio equals to the ratio between the angle's legs. We are relating to the angle that has been bisected by angle bisector AP. And the angle that has been bisected by angle bisector AP is angle OAE. And the legs of angle OAE is AO and AE. And the ratio between those two legs is AO over AE. So that ratio between the legs, the two legs, that is AO over AE, equals to the ratio that angle bisector AB divides side OE. And that ratio equals to OP over PE. In conclusion, OP over PE equals to OA over AE. Here OP equals to 3 units, AO equals to 6 units. So here OP is 3 over PE equals, and OA equals to 6 over OE. So in conclusion, according to equation number 1, 3 over PE equals to 6 over AE. We divided this equation number 1 by 3, and also we multiplied by AE, and we found out that according to equation number 1, 3 over 6 equals to AE over PE. 6 over 3 is 2, so according to equation number 1, 2 equals to AE over PE. We multiplied equation number 1 by PE, and found out that AE equals to 2 times PE. Okay, here, so AE is twice as long as PE. We define PE as A, here PE equals to A according to our definition, and also in the original drawing, PE equals to A according to our definition. And we substituted PE in equation number 1 by A. So A equals to 2 times PE, that is A, that is to say A equals to 2A. According to equation number 1, AE equals to 2A. And P equals to A according to our definition. Okay? Then we continued to focus on the right triangle AOE, and we actually implemented the Pythagoras theorem on the right triangle AOE. So I copied the right triangle AOE in a new page and we implemented the Pythagoras theorem on the right triangle, triangle AOE. AO equals to 6 units according to what is given as the question. AE equals to 2A according to question number 1. And here you can see from the drawing that OE equals to 3 plus A. Again, OE equals to 3 plus A. So you can write here that OE equals to 3 plus A equals to 6, and A equals to 2A. We implemented the Pythagoras theorem on this right triangle, triangle AOE. According to the Pythagoras theorem, we found out that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AE squared equals to AO squared plus OE squared. AE equals to 2A, so A squared is 2A squared. OA equals to 6, so AO squared equals to 6 squared, that is 36, plus OE squared. OE equals to 3 plus A, so OE squared is 3 plus A squared. So in conclusion, according to equation number 1, 2A squared equals to 36 plus A plus 3 plus A squared. We open the brackets on both sides of equation number 2 and found out that 2A squared is 4A squared. That is equal to 36 plus 3 plus A squared. 3 plus A squared is 3 squared, that is 9, plus A squared plus 6A. 36 plus 9 is 45, so according to equation number 2, we found out that 4A squared equals to 45 plus A squared plus 6A. We subtracted A squared from this equation, equation number 2, and found out that 4A squared minus A squared is 3A squared. 3A squared equals to 45. A squared minus A squared is 0. 45 plus 6A. So in conclusion, according to equation number 2, 3A squared equals to 45 plus 6A. Here we divided this equation, equation number 3 by equation number 2 by 3, and found out the 3A squared over 3 is A squared. 45 over 3 is 15, and 6A over 3 is 2A. So in conclusion, according to equation number 2, we found out that A squared equals to 15 plus 2A. We subtracted 15 and also 2A from this equation, equation number 2, and found out that A squared minus 2A minus 15 equals to 0. So here we have the quadratic equation. The missing variable in this quadratic equation is A. So x equals to A. The coefficient A equals to 1, the coefficient B equals to minus 2, and the coefficient C equals to minus C. And here the general formula to solve a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, x equals to a, so we substitute x by a. So a equals to minus b, b equals to minus 2, so minus b is minus 2, that is plus 2, plus minus square root of b squared. b is minus 2, so b squared is minus 2 squared, that is 4. Minus 4 times a is 1, times c is minus 15. Over 2a, a is 1, so 2 times 1 is 2. So we found out that a equals to 2 plus minus. Inside the root we have minus 4 times minus 15 is plus 60, and 60 plus 4 is 64. So we found out that a equals to 2 plus minus square root of 64 over 2. The square root of 64 is 8, so in conclusion we found out that a equals to 2 plus minus 8 over 2. So here we will have two solutions that are possible for a. The first solution for a is a equals to 2 minus 8 over 2. 2 minus 8 is minus 6. Minus 6 over 2 is minus 3. Minus 3 is a negative number. So according to the first solution, a is a negative number. But here, a equals to side PE. So a is a length because it is equal to side PE of triangle APE. So a is a length, it must be a positive number, it cannot be equal to minus 3, that is a negative number. So we cancel this solution, and we left only with the second solution, that a equals to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So in conclusion, we found out that a equals to 5 units, Therefore 2A is 2 times 5, that is 10 units, that is to say AE equals to 10 units, and PE that is equal to A is equal to 5 units. Okay? So what is the length of line segment BE? For the drawing it is very easy to see that BE equals to PE minus PB. Again here, P equals to PE minus PB. P equals to 5 units and PB equals to 3 units. This is the radius of the semicircle. So in conclusion, we found out that B equals to 5 minus 3, that is 2. So here B equals to 2 units. Then we found out the length of line segment CE. For the drawing it is very easy to see that CE equals to AE minus AC equals to CE. Again, AE minus AC equals to CE. Okay, again, here, C equals to AE minus AC, AE equals to 10 units, and AC equals to X. It is the line segment that we are looking for. So in conclusion, we found out that CE equals to 10 minus X. Then we extended the quarter circle to a circle. So we created here this circle, and we extended line segment OB by straight line until it touches the circle at this point, point M. Point M is the touching point of the extended line segment OB in the circle. So what is the length of line segment OM? The length of line segment OM is point O is the center of the quarter circle, that is also the center of the circle. Point M is the point on the circle itself, and this is exactly the definition of a radius. That is to say, OM is the radius of the circle itself, that is also the radius of the quarter circle, that is equal to 6 units. Then I presented to you rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, then the following equation is true. So here we have chord AB that intersects with chord CD. Again, chord AB intersects with chord CD. At this point, point P is the intersection point of chord AB with chord CD. So those two chords intersect with each other outside the circle because point P is located outside the circle. So in this case, the following equation is true, that PA over times PB, PA times PB equals to PC times PD. Again, PA times PB equals to PC times PD. Okay, so we can implement rule number 3 in our drawing. Why? Because in our drawing we have chord AC. This is chord AC that intersects with chord MB. This is chord MB at point E. Again, chord AC intersects with chord MB at point E. At point E is the intersection point of chord AC with chord MB. Therefore, we can implement rule number 3 in our drawing. According to rule number 3, we'll get it. So I'll repeat again. Here, chord AC intersects with chord MB at point E. So according to rule number 3, we'll get that EC times EA, again EC times EA, equals to EB times EM. Again, EC times EA equals to EB times EM. Okay, EC times EA equals to EB times EM according to rule number 3. Okay, this is the implementation of rule number 3 in our drawing. CE or EC equals to 10 minus X. EA equals to 10, EB equals to 2, and EB equals to 2, and EM is the long line segment. EM, what is the length of EM? EM equals to MO, that is 6, plus OP, that is 3, plus PB, that is 3. So 6 plus 3 is 12, and 12 plus 2 is 14. So in conclusion, we found out that EM equals to 14. So according to this equation, 2 minus X times 10 equals to 2 times 14. 2 times 14 is 28. So here, 10 times 10 minus x equals to 28. We divided this equation by 10 and found out that 10 minus x equals to 28 over 10 is 2.8. Here we added to this equation x and we subtracted 2.8 and we found out that x equals to 10 minus 2.8. 10 minus 2.8 is 7.2. So in conclusion we found out that AC that is equal to x, it is equal to 7.2 units. Here AC that is equal to x, it is equal to 7.2 units. So in both methods we found out that the length of line segment AC that is equal to x is 7.2 units. Okay, thank you very much.